Hello, I would like to talk about analyzing the effect of diverse gaze and head direction on facial expression recognition with photoreflective sensors embedded in a head-mount display. Facial expression is important for communication in physical and virtual environments. In a virtual environment, a user wears a head-mount display and emerges into the virtual world through an avatar. To transfer the user's facial expression to an avatar, it is required to recognize facial expressions with devices such as cameras. However, most facial parts of the HMD user is hidden by the display. To recognize the HMD user's facial expressions, photoreflective sensors have been leveraged. A PRS consists of a photodiode and a phototransistor and allows to measure the distance between the sensor and the skin. Several studies embedded the PRS into an HMD to capture the facial geometry and learn the sensor values with a machine learning model to classify facial expressions. Since the PRS are sensitive, the sensor is affected by the eye movement and the subtle shifts of the HMD. Previous studies using PRS showed that gaze gestures could be detected and head posture affected the recognition accuracy. Their results suggest that gaze and face direction affect FER or HMD users using PRS. This paper analyzes how gaze and face direction affect the PRS-based FER. We set 3 research questions. RQ1 is, does having a diverse gaze and face direction dataset increase recognition accuracy? RQ2 is, does selecting a direction classifier to correspond with the current directional information produce a better accuracy than using a generalized classifier for all directions? RQ3 is, which facial parts are affected by the diverse gaze and face direction? To address these RQs, we conducted 6 experiments. Prior to the experiment, we collected the dataset of facial expressions when the participants changed gaze and face directions. At first, the participants look at the gaze point by moving their eyes or turning their head. Then, the participants formed 5 facial expressions. While forming facial expressions, we collected the sensor data with facial sensing device. The gaze point appeared at 21 locations, since we collected the dataset. Using the dataset, we conducted 6 experiments to address the research questions. Each experiment had several conditions. In each condition, we divided dataset into different training data and test data. In all experiments, we evaluated the within-user classification accuracy. In the experiment 1 and 2, we investigated how gaze and face direction affected FER. We set 5 conditions. Condition center was used in the previous studies. Condition O was set to address RQ1 and the condition vector was set to address RQ2. Also, we set condition horizontal and vertical to figure out which directional change affected the FER. This is the result of experiment 1. The classification accuracy in condition O was the highest. It suggests that single classifier trained with the data of all gaze directions significantly improved the performance. Also, we compared the accuracy of inner 9 gaze points and the outer 12 gaze points. Statistical tests showed that condition center had significant differences in the accuracy between inner and outer gaze points. Therefore, to make the classifier robust to gaze direction, the dataset of diverse gaze direction should be collected. This is the result of experiment 2. Condition O achieved the highest accuracy, so it suggests that the single classifier trained with the data of all face directions significantly improved the performance. And we compared the accuracy of inner 9 gaze points and outer 12 gaze points. Statistical tests revealed that the condition center had significant differences in accuracy between inner and outer gaze points. Therefore, we considered that collecting the dataset of diverse face direction could improve FER. However, experiment 1 and 2 results was affected by the reproducibility of facial expressions. Since humans make different facial expressions every time, the number of training data could increase the accuracy. However, experiment 1 and 2 conditions had different number of training data. To explore the effect of only gaze and face directions, we conducted experiment 5 and 6 later. In the experiment 3 and 4, we investigated which facial parts was affected by gaze and face direction. To explore it, we grouped the sensor into 4 groups based on the location. We evaluated the classification accuracy when the machine learning model was trained with each sensor group. The training and test data condition was condition center in experiment 1. The experiment 3 result is on the left and the accuracy for each gaze point was on the right. Condition eyebrow achieved the higher accuracy, but the accuracy of the upper gaze points were worse than the bottom gaze point. Therefore, we considered when the participants looked at the upper gaze point, the eyebrows were lifted, facial expressions deformed, and that caused a decrease in accuracy. The experiment 4 result is on the left and the accuracy for each gaze point was on the right. According to the right figure, condition outer eyes, nose, and the cheek resulted in differences in the accuracy between the upper gaze points and the bottom gaze points, but condition eyebrows resulted in little difference. We considered that face direction did not affect the upper facial part around the eyebrow since the forehead is hard. Experiment 5 and 6 investigated how only gaze and face direction affected FER. In this experiment, we extracted the same number of training data in all conditions to remove the bias or reproducibility of facial expressions. We set 3 conditions. In condition center 21, we gathered training data from the 5 gaze points around the center. In condition O21, we picked up 1 session from each gaze point. In condition vector 21, we extracted the training data in the similar way as condition center 21 and calculated the classification accuracy of inner 9 gaze points. The experiment 5 result is shown on the left and the experiment 6 result is shown on the right. The statistical test showed the condition vector 21 achieved the highest accuracy in both experiments. It suggests that the building classifiers for each direction significantly improved the classification accuracy. Statistical tests found that experiment 5 results showed that accuracy in condition vector 21 was significantly higher than condition O21, but in the experiment 6 result, there was no significant difference between condition vector 21 and O21. Therefore, it implies that face direction had a small effect on FER than gaze direction. Through the experiments, we revealed that gaze and face direction affected FER. We addressed each RQ with the experimental results. Regarding RQ1, the results of experiment 1 and 2 show that training with dataset of diverse gaze and face direction increased FER accuracy. For RQ2, the experiment 5 and 6 showed that building classifiers for each direction improved the accuracy. In terms of RQ3, the experiment 3 and 4 found that gaze direction affected the upper facial part and face direction affected the lower facial part. Therefore, in RPS-based facial sensing, it is important to capture the entire facial movements. Conclusion is as follows. Thank you for your listening.